Hey everyone, welcome to the Database and AI module of the Azure Masterclass V2. Now I recently created a new version of my study cram for the DP900 exam. So that would cover a lot of what I would normally go through in this module. I also have an AI 900 study cram. So rather than duplicate those videos, and I recommend you watch both of those to get a good grounding on both the database and AI features in Azure, I'm going to cover at a higher level the sum of the services so you get some idea of what's available when I might use them. So we're going to look at the types of data, the database offerings, and then the machine learning and AI and what's the difference between those. And obviously AI is quite a big deal. Currently we hear about it in the news. So I want to talk about the different types of data structure first. And a huge one we always think about is relational. We have the idea of some requirement for online transactional processing. This might be part of a primary business computing solution. I want to do lots of create, retrieve, update, delete operations. They're high volume, they're fast access for querying, and data is commonly normalized in some kind of structure to enable this to properly function. So if we were to think about this, and let's start off with then the idea of relational. And this is, again, an example of some normalized data. So with that normalization, and with the relational, there's relations between the various types of data. It's following the relational model that's been around for a really long time. The goal here is we have some defined schema for a table. So I can think that I have a table, and this table follows a certain schema. So that schema defines the types of columns that we're going to have. And those columns can be thought about as properties, attributes of some entity that we're going to store. And the rows, well, each row is an entity of the type of this table. So we'll think about grouping things together of the same type that have the same common properties. So there'll be a whole bunch of columns. And the way the data is actually stored, now there's a separation between the logical and the physical structure, but physically it's stored in a row-centric manner. So it goes across, so hey, name John, age, weight, address, whatever, it will store it this way going across all of those datas. And it is normalized. So the data, no matter how it came in, now follows a set structure. Each of the columns, those properties are of a specific format. If it's a date, for example, it will follow a certain criteria and structure to make sure. That normalization will also help deduplicate because I'm going to have a table of each type. So this table, for example, could be my users, just as an example table. Now, if this was at work, those users may work in certain offices. Rather than have the office address next to every user, which would be a huge duplication, well, in this normalized way, I would have a different table. Let's say table 2, so that was table 1. Again, with its own schema, this time this might be offices. Now, its properties are going to be very different from that of a user. Its property might be an office code, so an identifier for it, street address, state, and maybe GPS coordinates, whatever that is. So it's going to have its own set of properties, its attributes, and then it will have entities for each of the physical locations that the company has. And then there's going to be a key. So there's going to be a primary key. So for a user, its key could be the employee ID. For an office, maybe it's a location identifier. And what I will do very commonly is I will reference an entity in another table from my table. So maybe this is, hey, my office ID, and my office ID would actually be a foreign key that references the key of the offices table. So I'm not having to duplicate all that data. I'm just going to reference it. Imagine it was a store. I might have a users table. I might have a set of tables around the different offerings I have in my store, my inventory. And then a separate table would be orders. And an order would reference the user that ordered it and that entity, a certain piece of inventory that would make up that order. So I can think I'd have these relationships between them. So this would be a foreign key. But the whole point around this is we have this set schema, we're normalizing the data, we're removing any kind of duplication. And some good examples of this would be things like SQL Server, Postgres, MySQL. There are many others that follow this relational database, and that's the key point of these. So if I have some business function, I'm creating these maybe very high volume, I'm doing transactions, those CRUD operations, I'm reading and writing. This is the type of system I would commonly use, an OLTP, this online transactional processing. There are also other types. So if we go over here, we'll also hear about non-relational models. So with a non-relational model, there's different types. Now this might be heard of as NoSQL or not only SQL. And it's not stored in that strict schema-based tabular form. I have flexibility here. So one example would be documents. It could be self-describing, a JSON document, an XML document, even YAML. There's some component of the document that describes what the actual attributes would be. If I was to jump over actually for a second, let me just quickly have a look in my VS Code. So if I looked at my VS Code here, this is an example of a JSON file, and there's no fixed structure to it that's inherent to JSON or any particular document, but you can see it's self-describing. I can see, for example, there's a new entity surrounded in the curly braces, and it's defining what are its various attributes. So it's got a first name. I can see, oh, there's an address. An address is actually made up of multiple components. But it doesn't have to always be the same. There's another entry, but this one also has pets. Hey, Superman's got crypto. It has powers, which is multi-valued. So there's different options I can have. It's not some fixed set schema, but it's self-describing when I actually look at those elements. So we can have things like JSON. Also, there's key value. So there's some kind of key, and I'll show these in a second, that's maybe a partition. It's a way to identify a certain element, and then it has a certain value. This enables me, with this key, I can shard or spread my data over multiple logical and physical actual partitions, so it'll be very, very highly scalable. I can get very, very high performance. There can be columnar, where if we remember, the relational database stored it as rows, name, age, weight, address, whatever. With this column-centric model, the data is actually stored as columns. That gives us a lot of efficiency, which we'll see in a second. And then graph. There's some idea of nodes and really links between those. So if we quickly look, so if I shift now over to the idea of non-relational, so it's not just this very strict, hey, I've got this schema, I've got other types of data. So now let's go, we'll do non-relational. And again, you could hear it referred to as NoSQL. So not only. And there are different types. It's not forced to that strict schema-based table structure. So one of the very common ones is documents. And there are many different options for this. And the whole point is they are self-describing. I can look at a JSON document and I can tell what those elements are. So JSON is a very, very common example. It could be XML. Again, it could be YAML. But it's that idea that there's no fixed structure to it. We have key value. Now, key value, often when you look at it, will look like a table in a relational database. But the point is there is no fixed schema to that. It is just these key value pairs. Now, for a certain key, I might have multiple entries, multiple different values. So when I look at it all together, well, it looks like a key and then a whole bunch of attributes. But they're individual entries in our system. If we were to go and look really quickly, so a good example is Azure Storage has, now it's called tables. But if I was to go and look at an Azure Storage account, and I'll actually look at its storage browser so we can visualize this, I have a test table. And it's showing me these key value pairs. Now, as you look at these entries, you're there, well, this looks a lot like a table. It looks like there's some fixed structure. But there is no schema. There is nothing that defines hobby and children and car and age and color or alias. None of those things. Each entry just has a partition key and a row key that uniquely identifies it. That partition key can help me, again, partition the data and spread it out. But when I create a new entity, it's showing me ones that have been previously used just to maybe help me. But I don't have to use those at all, and it won't create those as null values. They just don't exist for this particular entity. But I can add any properties I want. I can add a brand new one. Favorite food. If I could spell. Favorite food. And it's a string, and I'm going to say, okay, pizza. And for this one, I may just say, I don't know, Thor, whatever I want here. Was it user? Well, actually, it's user, correct? So user Thor can be the row key. I'm just making these up. So it's created another entry at the bottom. I can see the timestamp doesn't have any of those other attributes. It's just key value. That's all this is. It's completely different from that fixed schema. Again, when I look at it, it may look a little bit like a relational database, but none of those constructs apply to it. I'm just creating these key value pairs. It just happens to look a bit like a table. Then we have that column focused, the columnar. And once again, if you just look at it, it will maybe look very, very similar. But the point here is that it's storing it as the columns. So it would be a storage of name. So it could be Thor, Steve, Oliver, Eddie. They would all be stored next to each other. Then maybe it has age, date of birth, whatever those things, but it's stored this way. And the benefits this gives us, if you think about it, is, well, columns, certain attributes or properties of some object are likely to have very, very similar values. Well, that means it's going to compress very, very nicely. If I'm trying to perform operations that just maybe summarize on a particular column, well, it's organized by that column now. I don't have to go and scan through all the records, just look at one column. It's stored by that column. So operations, when I care about something at the column level, is going to be very, very efficient for me. It's going to be self-indexing because, hey, it's already based and stored around the particular attribute. So there's a lot of benefits to do this. So Apache Cassandra, Cosmos DB has columnar capabilities. And then we have graph. And the whole point of graph is it's describing relationships between things. So I would have multiple nodes. So I might have a node of type person. And this could be John. And then there could be another node. And maybe this is of type office. And then what I have is an edge, which is the relationship between them. So in this case, it might be works at. There might also be another node, which could be another type of person. And this time it's Julie. and it could be, again, it's another edge, and this maybe is reports to. So John reports to Julie, and then Julie also maybe has a relationship. Maybe we call this home is the actual specific node instance. And maybe this is, well, Julie manages home. So I report to my wife and she manages the house. She's in charge of everything. So that would be an example of a graph. And so graph is really powerful when I care about the relationships between things. Because now I can just go and trace along those edges to find out. If you look at things like Facebook and Friends, that cares about the relationships between things. So MongoDB, using Gremlin to interact is a really good example of this. And then, of course, there is also, and I'm not going to really focus on this at all, but you have unstructured. So with unstructured, it's just to us and to the general type of data, it's just bits on a disk. So it's just bits. Now this could be a binary large object. What's actually inside that? It could be media. It could be a JPEG, could be an MP4, an MP3, an AVI file. It could be a document, like a PDF file, for example, docx, whatever that might be. It could be anything. I can store anything in unstructured. Now, certain applications will understand the format within this whole sequence of bits, but it's not a general type of, hey, data that I have in some kind of database. It's just stuff that I'm storing that I need available to me. So that's really the point of all of that. So they're the key types of data that we may have in our environment. Great. And your application, if it's some business function, and again, it's doing that more transactional, it's a very high chance it's going to use a relational database. It may also use, depending on its requirements, it might use that NoSQL, so a non-relational. It really comes down to the types of interactions, the type of functions I need to perform. So what about databases in Azure? Well, I can install anything inside a virtual machine. But the whole point is, if you just install it in a VM, you're responsible for everything. The OS underneath, but then also if you think about, well, the database software I have to install, the database software I have to patch, database software I have to back up, worry about its high availability, worry about its disaster recovery, worry about the tuning. And I'm going to say, well, maybe not, because there's a little bit of a caveat to some of the solutions. So if we go back and we think about, well, okay, so a database just in an Azure VM. I can absolutely just take an Azure VM. Remember, this is infrastructure as a service then. And if we think about that infrastructure as a service, remember what's the line of responsibility? Because it's responsibility we care about. The responsibility here is Azure is responsible for, hey, the storage, the network, the compute, and the hypervisor. You are responsible for everything above the line. So now in that IaaS world, you are responsible for the operating system. And if we're thinking about a database specifically, you're responsible for the database. And for both of these things, for both of them, well, obviously I have to think about the install. Now, for the OS, there are images that have operating systems pre-ready, or maybe I'm creating my own image. There are images that have databases pre-baked in as well with pre-configured things. So in the marketplace, there are things that can help me get going, but I'm responsible for picking that. I'm responsible for thinking about the patching. I'm responsible for thinking about maybe even upgrades. I'm responsible for the backup. I'm responsible for the high availability. Potentially I need disaster recovery. Remember, they're different. High availability, we typically think of within a certain location if there's some node or rack failure, it just carries on working with zero data loss. There's synchronous replication. Disaster recovery is another location. It will be asynchronous replication. There might be some data loss in an unplanned scenario. So there's tuning, there's all these different things that I am responsible for. But a key point here is, though, I can use anything. I am not limited to a particular type of database. As long as the vendor of that database says, yes, we support Azure, the world is my oyster. And pretty much all major database vendors today will let you run, because they don't care. It's pretty much invisible to them what this underlying hardware or hypervisor is. They just see a full OS. They can do what they want. So obviously things like SQL Server, Postgres, MySQL, Oracle, the regular Oracle I can run in here. But I have all of these different responsibilities. Well, normally. So let's start off with some examples of services. Now, an obvious one, if we're talking about Azure, well, Microsoft have SQL Server. And there's actually a lot of different offerings available for SQL Server. And the first one, well, is just a SQL virtual machine. Now, there are images that have SQL Server just pre-baked into an image that I can install. There are even container images. I can run SQL Server in a container. I can run it on Linux. But instead of me just having that SQL installed and then it's washing its hands with it, there's the ability to have an agent extension. And the agent extension can give me different levels of additional functionality. So let's look at SQL Server. So if we take SQL Server as our first example, I can have it available in Azure in many different ways. So the most simple one, well, the most basic one for us to understand is, hey, SQL in a VM. It's probably not the simplest one. The simplest one is where it's just offered and managed for the most part for us. But in a VM, sure, it's this model. But what I can then do is I can add an agent extension. If you take one of the images in the marketplace, it's going to have this for you already. And this agent extension can actually run in two modes. So there is a lightweight mode. Now, both of these modes are free. I want to stress that up front. And the reason lightweight mode was popular initially was to go to the full mode, you had to restart the SQL service. So there was some impact on the availability. That is actually no longer the case. So I can go to the full mode and it doesn't impact the availability of SQL. However, there still is a lightweight mode. All this really lets you do is, well, I get inventory, I get information about it showing in the Azure portal through the RESTful APIs, and I can do a skew change on the SQL, just from a licensing perspective. But I can also have the full mode, and I can move. So if I was running lightweight, I can absolutely upgrade. And once again, they are both free. There is no cost for this. Now, once I get to the full mode, I get a whole set of other capabilities added to me. So for example, if I think about the patching, when the full mode, I get auto patching. Now, Azure already has things to help patch the operating system. That's going to patch the database as well. I get different options around the storage configuration of the database. So I could add additional disks. I can help change the performance. I get integration with Azure Backup. I get integration with things like Azure Key Vault for various types of secret management and keys. I get integrated high availability capabilities, integrating with always-on availability groups. And there's a whole set of other stuff I get. There's a least privilege mode available. And there's Defender for Cloud recommendations will get surfaced up. I can enable this at a single instance. I can enable it in bulk through a script. I can enable it at a subscription level, so it will turn this on for my existing SQL in a VM, but also future ones as well. So there's many different ways I can use this. So that might be the most easy to understand how I'm going to run it in a VM. But then there's a whole bunch of other options, which then move into the real platform as a service type offerings. It is considered a PaaS offering because a database on its own is not really providing a business function. I'm going to write some application that's using this, which then in conjunction with the database provides some business value to me. So Azure SQL Managed Instance. So Managed Instance, well, it's fully managed, but what it's going to do is it's going to run inside my virtual network. And I'm going to sort of consider this a little bit of a progression. So at this point, though, if this was IaaS world, we're absolutely now, if this was an IaaS scenario, this is very much moving into PaaS scenarios. We think of PaaS as evergreen. It's automatically. So evergreen means we're going to get the new functionality added for us automatically. I don't have to think about upgrading SQL. It's just going to do that for us. So we like this because it's evergreen. And this is consistent across all of them. We're going to get this cloud cadence of new functionality. But the first offering here, that was in a VM. So this is going to be SQL MI, Managed Instance. And a big differentiator here is SQL MI, well, this is in your VNet. So it's deploying into a delegated subnet inside your virtual network. So it's going to integrate very closely with other things that are connected to or in that virtual network. And a huge benefit here is it's a dedicated set of instances running in VMs in your virtual network. So if I was running SQL already, and I want to move my application into Azure, and I'm worried about certain features being available. Hey, I need the service broker. I need the SQL agent. I need the common language runtime. I need the CLR. There's a whole bunch of other things. The huge benefit of this is it's near 100% compatibility with regular SQL Server. Because when we move into some of the other PaaS options, not everything is available. But this is going to give me near perfect compatibility with regular SQL. So if I'm moving a workload, this is a really good option. Excuse me. One of my options I do have around SQL MI is there is the option that I can do an instance pool. So again, it's dedicated resources, and an instance pool is a set of resource that I'm defining, provisioning. Then I can create different size managed instances within that. Maybe I want some very small ones. I'm moving lots of fairly small SQL servers to Azure. Maybe I only need 2 virtual cores. I create that idea of this set of instance pool with resource, and I create multiple managed instances inside it. And then within a particular managed instance, I can have multiple DBs. So I can create multiple databases per managed instance. And when I think about that compatibility, this document goes through some of those examples. So here I can see it starts talking about what I can do. So let's look for some. So the left column is Azure SQL Database. The right column is Azure SQL MI. So if we look for some no's, so I can use the backup command. That's probably not a big deal. Built-in functions. Well, regular can do most, just yes for SQL MI. But one of the more interesting ones is this, common language runtime. I cannot use that with regular SQL PaaS, but I can use it with SQL MI. I can do cross-database 3-part name queries. There will be other things if we start looking. So cross-database transactions, database mail I can do. There'll be things around the agent. If I keep, but there's a whole bunch of different things. Now, it depends what features you need. But if I am using things like, hey, the SQL Server agent, I get that capability. So there's different things available depending on what I need. Now, if I was writing my app for the cloud originally, I probably wouldn't leverage those things. I wouldn't need them. But it's all about the idea that, hey, I've got something already and I'm taking it, I'm moving it to the cloud. Then obviously there's Azure SQL Database. So Azure SQL Database is that, I guess maybe what we think of the original PaaS offering for SQL Server. It's that fully managed PaaS solution. Now, it can still integrate with my network. There's still the ability to use things like private endpoints, but it's not deploying inside my virtual network. There's certain sets of shared infrastructure and gateways that take the original connection and then distribute it to my elements. So then we just have, and it's just called regular SQL Server. So if you just see SQL Server, it's talking about the PaaS. So I would think of full PaaS, but once again, it can still integrate into my virtual network through things like private endpoints. Now for SQL Server, there's different offerings. So there's a serverless offering. And the serverless, you see this in a number of services. The serverless is all about typically auto-scaling based on the load. I don't have to have some pre-provisioned set of things I'm paying for. It can also typically be stopped if it's not required. And there'll be different types of service this may or may not be available for. There are single instance. So it's a single database on a set of defined resource that I'm paying for. There's things like elastic pool. So elastic pool is where I'm going to define a set of resource and I can create multiple databases inside that elastic pool. Where this would be useful is imagine I have multiple databases and they're busy at different times. Or they might need to burst occasionally. So with single, I define a set of resource for that database. It's always got that amount of resource. Well, with the Elastic, it's a shared set of resource. So if I do have those scenarios where some databases are busier at different times than others, I'll get a better utilization of my overall resource. So if I thought about, well, this is my set of capacity, and let's say blue is one database, and it's like maybe that's its resource need, but then maybe I have another database, and its resource need is like busier here, and then it maybe gets quieter there. There's some overlap. And then maybe there's another database on that same set of hardware, and it's generally a fairly low, but maybe occasionally peaks. If they're an elastic pool, as long as they're not all peaking at the same time, hey, I'm going to get a better utilization overall of my resource compared to single, where single is just the resource is reserved for a particular instance of a database. So that's where elastic pool can be really useful. There's also, for SQL, there's hyperscale. Now, as the name suggests, hyperscale is all about this idea of really, really huge performance, huge scale. There's a primary compute node where I submit my operations to. There could also be read-only secondaries for interaction. Hey, I want to do analysis. Then there's a completely separate set of servers, they're called page servers, that actually store and interact with the data. So that gives me this huge scale, this huge performance, because I'm separating now the request and the handling to the actual storage and running certain types of queries. So that we have a hyperscale offering as well. Now for both SQL Server and SQL MI, there's different service tiers. So for both of these, we have service tiers. And this changes elements of their architecture. So I can think about an idea of, well, there's a standard. You might hear it called basic, you might hear it called general purpose. The whole point here is there is a primary. So there is a primary instance running. And what it will typically do is that primary instance will separate out its storage. So it may be, in Azure storage, a managed disk. So it separates out the storage. But if something happens to this node, well, there are some kind of spare boxes hanging around. And so if this box went up in flames, this would kick into life. And then, okay, I better get doing something. It would go and connect to that storage and start offering your service again. So there will be some downtime as that has to take effect. Then there's also an idea of premium. business critical. So here it's a very different model. There's still a concept of obviously there's a primary, but the data is local. It's not stored on some separate storage. There'll still be some separate backup, but what then happens is this primary is replicating to, we have the idea of passive. So there's standby, but it's connected to, I'm going to say secondary, and they might be used for read purposes, and there's actually been multiple of these. There's another one over here. And they have, again, their own local copy of the data. So these are constantly replicating. And now you can imagine if there was a problem with the primary, these are going to start up that much quicker. It's ready, it's using these functionalities. There's the ability for both of these. So optionally, I can support availability zones. So zone redundant. It can spread these things. The disk in this model would be a ZRS disk. So that disk is available cross zone. Here, these instances would be spread across different availability zones. And if we look, I think I've got it on. Actually, let's go to the next one. Hyperscale. So I mentioned that already, but if we go and look, if it lets me, come on. I'm sure I'm missing something about the consistency of what you have to do to make that link work. So this shows the models. But here we can see, hey, for that business, sorry, the general purpose, the basic, the standard, we have the idea it's a primary, but the disk is going to some separate storage. And then there are some spare nodes. So that, and again, there's that separate gateway ring. If I go and look at zone redundant, all those spares are in different zones. If I look at premium, well, it's not doing that anymore. I have the primary replica, and then I have those secondaries, but it's local data, local logs, but then sure, the backup, that still goes to some durable separate storage. Then of course, hyperscale, well, it's separating the compute from the page servers that actually then go and talk to the data. So we have different models, and what we're going to use is really going to depend on, well, what's the criticality of our solution, because they obviously cost different. It costs me more money to have all of these replicas standing around waiting, but also maybe I want them. I've got some analysis workload I could run against those secondaries. Go away. So that might be what I want. Hyperscale, hey, I've got some huge performance requirement. And for a lot of these, I can buy them in different ways. There's, especially on some of the standards, there was a distributed transaction unit, a DTU, where it was a blend of the CPU and the storage. Or I can now separate out the cores and the storage I want and just pay for exactly what I need. So I get more flexibility. So there's different methods I can use to actually go and get these solutions, and I pay for exactly what it is I need for any different scenario. So that's really the key point about how I want to use these. So that was the SQL Server. Let's carry on. So there's scale capabilities in all of them. I can change the particular model. I can change the number of instances I've got. I can, for some of them, actually change the number of nodes. So I can have multiple read replicas. I can potentially create replicas in other regions, for example. So they have that geo-replication. So I think it's 4 read replicas, except for hyperscale. So I can go and add replicas to other regions. And remember from our resiliency models, I might want a replica in another region, maybe for DR purposes. But it may also be I have an application running in another region, and maybe it's very read heavy. Most things are very read heavy. So I could have a replica in another region to read from, but if it had to write, then it would go cross region to perform those writes. I have to think about that write-read consistency, but that may be something I want to do that meets my requirements for whatever my application is and how it's working. For SQL MI, I would create another MI instance in the other region, and then I would set up via a failover group it as a replica. If need be, I could promote it up to a primary, and it would break that replication. There are long-term retention configurations, there's backup integration. I can even run SQL MI on-prem through Azure Arc. Remember, Azure Arc lights up different services with Azure capabilities. So if I have Arc-enabled Kubernetes, so any CNCF compatible Kubernetes environment, I can deploy many data services. And one of those is SQL MI, also Postgres for Azure Managed. So this is one option. And I would think of, hey, SQL Server, I'm using SQL Server already. I know SQL Server, there's capabilities of SQL Server, the APIs of SQL Server. I want to use a SQL Server environment. Fantastic. I can absolutely run SQL Server in Azure. But maybe I'm not. I'm maybe using an open source solution. Postgres, MySQL, MariaDB. These are all going to be based on the community editions, because there are also often premium editions by certain vendors with maybe additional functionalities supported by a certain vendor. These is based on the free community open source versions of the software. Now they are enhanced with Azure functionalities. If you go and look at, for example, Postgres and MySQL, they've added different types of replication technology and key management and encryption features, and they bring in certain functionalities around brokering, for example. So Azure does enable and light up additional things. But there are various offerings around these. And so I want to quickly talk about what a couple of those are. So if I think, actually, what's my next point? So flexible. Flexible is a big direction for what's happening with both Postgres and the MySQL offering. So if we shift for a second, so if I find somewhere else to draw. So this is still PaaS. So these are still considered evergreen. Now maybe I have to tell it, hey, I want to go some version. Sometimes it can do big upgrades for me. Sometimes it's just going to do the minor upgrades for me. But we're still in the PaaS world. But now instead of it being SQL Server based, which is a solution from Microsoft, now we're instead going to be, what color shall I use for open source? Well, we'll use that color. So now we're going to be open source. So we have open source based. And once again, it's using the community editions. Now, the first one I'm going to talk about is Postgres. Now, again, remember, these are still fully managed. These are PaaS solutions. I'm not connecting to the operating system. I'm using this as a PaaS fully managed offering. So Postgres. There's a number of different offerings available. There's something called single server. This is legacy. This has no future investment. If we actually look for a second, so let's jump back to the other slide. If we look at flexible just on here, if it will open for me, there we go. If we look at the versionings as Postgres as an example, if we look at single server only supports up to 11. Whereas flexible, hey, that's 14, 13, 12, and 11. So it's very clear to see right there that single server is not getting any investment. If I want to be using the newer functionalities, the newer versions, single server is not the way to go. Single server used a container type technology. It wasn't regular containers, but it was a kind of model where it was certain shared components, which limited a lot of configuration options. And so what we now have is the idea of flexible. And everything I'm going to say about flexible applies to the flexible MySQL as well. So this is VM based, i.e. my particular instance is a complete VM for me. Now, because it's VM based, that includes things like using the B series. Remember, B series is burstable. So maybe I have some workload that's normally fairly low amounts of resource it requires, but occasionally peaks up. Well, this is great because I'm paying a smaller price for that compute ordinarily, but it does have the ability to burst up if it's got some small window of heightened activity. Because it's VM based, I can also stop and start it. Once again, the attractiveness of that is maybe it's some batch process that needs to run against it. Maybe it's used for some development. I can optimize my cost. I can turn on optional high availability, where I have a second instance waiting that's getting the synchronous replication. It's there and ready for me. It's going to use the streaming replication ideally. It's warm, it's ready to go. There should be zero data loss. There's even auto failover capabilities within there. It has high configuration options. And what I mean by that is there are literally hundreds of settings I can configure for my Postgres or my SQL with this, whereas those were not available in the single because there were certain elements. It was a shared database instance. I didn't have that. There's also features, for example, called PG Bouncer. PG Bouncer is a connection broker. There's a finite number of connections I can make. PG Bouncer acts as a broker to connection requests. It enables a connection and then it distributes those through all of the requests. So I have that capability. Now there is also, there used to be a hyperscale offering. And there still is, it's just not called hyperscale anymore. So what we now have is Cosmos DB, which we're going to talk about later on, for Postgres. So what used to be PostgreSQL Hyperscale is now Cosmos DB for PostgreSQL. So the big deal here is it adds the Citus, this is another open source component, extension. And what the Citus extension does is it adds the idea of distributed tables. A distributed table, remember we talked about partition keys. It's going to let me spread the data over different partitions, over different instances of Postgres. So now I get a much bigger scale. I can get high performance because I can spread my queries, my operations, my data over multiple servers, and then aggregate the performance, aggregate the capacity of that. So this was formerly known as Hyperscale. It's now under the Cosmos DB umbrella. There is also, for example, Cassandra. There was a Cosmos DB for Apache Cassandra, that columnar type capability. So there's really three versions of Postgres. I wouldn't really use single, but definitely flexible. If I need that huge scale, I need those distributed tables. There's also reference tables. A reference table is where the data is replicated to all of the nodes. Maybe it's some common set that everyone needs to go and look up against. I still have those capabilities as well. Now for this, I guess I should point out that I can run this, funnily enough, in a single node mode, where it's just one node. That's good for testing, for getting started. But most of the time, you're going to run in a multi-node. And the multi-node breaks it down into two different areas. So there's going to be a coordinator node. That's going to take the incoming requests, and then it's going to send them to n number of workers, which is how I then actually distribute the tables, distribute the work. And I can move that way. So I can essentially upgrade. So I can start off with single, and then, okay, I've got it working, I understand what this is doing. Now I need to go and move beyond that. So that's the Postgres offering. There is also that Postgres for SQL, Hyperscale. There's also MySQL. There's also MariaDB. So to finish off our little picture here, so when I think of, I'll change my color slightly, I suppose. So that was Postgres. There's also MySQL. And MySQL and Postgres really have a common set of features in terms of Azure features. So this also has a single, but once again, it's legacy. The forward path is flexible. And all of those capabilities I talked about here, they apply as well. So kind of see above. Both of these support things like custom managed key. I can bring my own key for the encryption. They're both adding their support for multiple regions for resiliency. They both have support for Azure AD type authentication and then RBAC within the systems. So there's a lot of work around doing those. There's also MariaDB. Now MariaDB is a fork of MySQL. this only has a single mode. There's no flexible offering for MariaDB. When I think about using these, so MariaDB has really good Oracle compat. But so too does Postgres. Put my color back. So when I think about what one I want to use, it's going to come down to what is my application? Maybe I'm moving from Oracle to something else. Postgres is a very common target for that. MySQL is often part of the LAMP stack. So I'm creating some application. I've got Linux, Apache, MySQL, PHP. Obviously, the M is MySQL. So it's very commonly used as part of that combination of components as part of my all-up application. So all of these are part of this Azure managed database for MySQL, for Postgres, for MariaDB. So if I'm using one of these, if I want that open source based technology, I can absolutely do that with any of those options available. So I have a lot of flexibility in what solution I choose to actually use. What about non-relational? So we have Cosmos DB. This was built from the ground up. So if you look at all of the other solutions, SQL Server, MySQL, Postgres, MariaDB, Cassandra, they existed and they were taken and put in the cloud. And they were optimized for the cloud. There were things added. Cosmos DB was built for the cloud. I think it took some evolution actually from some of the Bing work in creating that engine. But this was designed for the cloud, designed for global distribution. And it has multiple models supported. It is built around partition keys to enable me to distribute the data. And it's got a configurable consistency. So, okay, what does that mean? So let's actually go up this time. So now we're going back to this idea of non-relational. So a non-relational, we're going to talk about Cosmos DB. Now, whenever I'm not going to get into all the theory. I talk about that in the DP900 video. But there's something called the CAP theorem. So CAP is the idea about, well, there could be partitioning. So there's some network issue between instances of servers. There's availability, I don't get an error response. And then there's consistency, making sure, hey, depending on which one I talk to, I get the same results. Well, there's another theorem that adds the idea that, well, what if there are no partitions, but I still have to pick between latency and consistency? Because often I have to pick one. I can't solve the problem of the speed of light. It takes time. And so I have to decide, well, what's more important to me and my particular workload? And it will vary. So if we think Cosmos DB is all about the idea that I can support multiple regions, well, those regions could be really, really far away. Do I want to ensure that no matter which copy I was talking to, I could always get a response and I can always work with it, I can make writes, and it would eventually sync to the other copies? I am going to allow some latency between the accuracy of the information, or do you know what? I need it to see the same thing. I'm really concerned about the consistency. And I have this idea of variable consistency because my use case is going to be different. Sometimes I may not care about a person over here talking to this copy, seeing the same thing as a person over here talking to this copy. As long as it catches up eventually, in fact, let's write that down. So if I have a variable consistency, I might not care. As long as it eventually catches up, great. At the far end of the scale, I might have strong. No, I'm going to take the latency. I'm okay with it running slower in my operations, but everyone should always see the same thing no matter where they are. Now, if I do strong, I cannot have multi-region write. Doesn't make sense. How can I write to multiple regions at the same time if I need strong consistency, i.e. they always see the same thing? And there's no benefit in multiple writer. They might as well just all write to the same one. So if I want strong, I can't have multi-region write. There may be a middle ground. I might say, well, do you know what? Doesn't have to everyone always see the same thing, but if I'm sharing a session, so I can have multiple things maybe in the same region, they should always see the same thing. There are actually some levels in between that as well. So if we go and look at a Cosmos DB database, it will actually show us some little examples of this. So let's close all these windows down for a second. So if I jump over to a Cosmos DB, well, firstly, I can tell it, is it multi-write or not? So if I do replicate data globally, I can turn on multi-region writes. I've got it disabled. Again, I could not enable that if I had strong consistency, because it doesn't make sense. Notice I can add on as many replicas as I want. I'm going to pay more money, but I can add any region anywhere in the world to have a copy of this. But then I pick a consistency. Now you'll notice I have 5. Strong, which we saw, which cannot have multi-write. Everyone should always see the same thing. Eventual, who cares? They can see read and writes out of order. Eventually, they'll all see the same thing. Session is very common. Hey, if I'm in the same session, everything used in that session should see the same order for writes and reads. Well, there's a certain amount of bounded staleness, how far I can go out. Hey, within a prefix, I should see the same thing. And it actually shows me a nice little picture. So notice session, it's talking about, hey, these musical notes are changing. Within the same session, so these are all session A, they see the same thing. But a different session, it might see some things differently. They're going to come in at a different time. If I picked eventual, well, everyone just sees different stuff. Eventually, it'll be the same thing, but no idea when. If I say strong, it's going to be the same. As soon as I do the write, they would then see that and they would read that data. There's no inconsistency between them. Bounded staleness, I give it a lag time. So what is the amount of time it's allowed to delay by? Consistent prefix, well, it really comes down to, I'm guaranteed just within that certain element that I'm having. You can see how it goes out. So what I'm going to pick depends on my app. There's really not a right or wrong. It's telling you, look, session consistency is the most widely used. It's really useful both in single region and in globally distributed applications. But I get the choice. That's really the key point of this. Cosmos DB supports many different types of API. When we looked at the whiteboard, remember we talked about, hey, look, documents, key value, columnar graph. Cosmos DB has these. So from an API perspective, I'm just going to use this same picture. So the APIs that Cosmos DB has for document, hey, it has SQL, it has MongoDB. For key value, it has a table API. For columnar, it has Cassandra. And for graph, it has Gremlin. So it's really powerful that I can use all these different types of NoSQL through Cosmos DB. If I'm writing a cloud-native application, and especially if I'm in this world where I really need to support multiple regions, and I'm trying to get past that challenge that I have with regular relational databases where there's only one primary, it's only one writable copy. This can be really powerful to light that up, enable me to go way beyond what I can do with regular relational database. So that's a key point of what this is going to give me. Encryption is really table stakes now, realistically. They all support encryption using a customer managed key. I bring my own key. That key would live in your key vault. There are now things in Key Vault that can auto rotate the key. For SQL, there's also transparent data encryption, but there's also things I can go beyond that. There's always encrypted where the encryption takes place at the client. So it's even encrypted in the database. So even a DBA couldn't see the data. Data masking is not encryption, but depending on my permissions, for example, a social security number, I could mask all of it except the last 4 characters. But it's not encrypting it, it's just what it's letting me see. TLS, again, is a must-have. Using TLS to encrypt the data between the client and the server. Some of these even have confidential compute. So the actual operations on the server, it stays encrypted at all times. Now, then we think about data warehouses and analytics. Remember all those data services we've talked about, they were all about that online transactional processing. There's some business function. It maybe is doing high volume transactions that are probably going to be smaller, fast access for querying. I'm normalizing my data. But then we have also a separate need. I have a separate need to look at historical data, maybe huge amounts of data, to give me some information, to give me some insight, to perform some analysis against. So you think of this as online analytical processing, and it's typically read-only. I'm not writing, I have a huge amount of data, I want to get some insight. So I want to get insight from my data, and this is often at the end of some data pipeline. I'm doing something, I'm reading data in, I'm doing stuff to the data, and then it's going to end up somewhere, so maybe I just have to store it, but often I want to get some useful insight from it. So I want to do some analysis, maybe using Power BI to get some nice dashboards and visualizations. So Azure Synapse is an example of a data warehouse solution. So if we think about and this is PaaS, so our solution here is still PaaS, but now we're moving outside of OLTP. So I guess I should really maybe draw another line. So now if I think about a line, if these were more about that transactional, now I'm thinking about the whole analytical processing. And the point now is it's going to be a data warehouse. And the reason we have it, yes, there may be a historical, I just have to keep it for a certain amount of time, but more likely I'm storing it because I want to perform analytics. And remember, the nature of the analytics with this OLAP is it's large amounts. So it's a large amount of data. My interactions are going to be read-only. I'm not changing the data. It's historical. So I have a huge amount of this historical data. So from a solutions perspective, this is Azure Synapse. Now, Azure Synapse comprises of actually multiple components. So Azure Synapse, yes, has the data warehouse. It has that big storage for all the data, but it also incorporates a lot of different elements that were previously different services. And while it worked, there was a fairly big burden on me to get them all configured to talk to each other. There was a fairly big burden on me to set up the security correctly, the relationships between them correctly. So Azure Synapse brings all of the different bits together. It has those different models, semantic models for how I might want to actually visualize and see the data. A data warehouse may denormalize the data. What? Remember, we normalized the data in a relational database. We normalized it so we didn't have replication of data. We had this concept of, hey, we normalize it, we get rid of duplication, we split it into different tables. That's great for this, how I want to be efficient with space. I want that very fast performance. But if I'm actually more interested now in just getting insight from the data, I may not want to have to go cross-table. It will slow down that processing. So when I store it in a data warehouse, I may denormalize it. I may actually rather have replication of data because that's better for me. The storage is cheaper. I'd rather store it multiple times, but it's going to speed up all my interactions with it. So that's actually a fairly common thing. So the schema for my data warehouse is optimized for data analytics instead of the transactional types of processing. I'll take duplication, so I'm going to get faster querying against it. So Azure Synapse has compute, it has storage, it has its own SQL pools. It integrates with services for different types of transformations, for data preparation, for different types of operations that I need to perform. So it's a complete compute and storage type solution available for me. And I guess in a way that's an interesting point. So if I think about, well, okay, so I said that there's data, it comes in somewhere, it does some stuff. Where is it coming from? What is making it? What is it putting in this data warehouse? There's a whole flow of things. So, data flow. We always talk about ETL or ELT. So extract, transform, load. But also you'll hear about extract, load, transform. So what does that mean? Well, let's just draw the picture. As a company, we have lots of sources of data. Where can I draw? Let's find somewhere. We'll go down the bottom. I'm trying to keep it roughly so I can put it on the handout afterwards. So I'll start drawing over here. That will make it probably a best place. Maybe it'll fit on a page well. So over here, I have multiple sources of data. Now my sources could come from anywhere. Could be on-prem, could be from a cloud, could be from a SaaS solution. But I've got some source. Now there's two types of source. I can think about batch. So a batch type is, well, it's some interval-based processing. So data is basically getting stacked up. It could be in files. And periodically I go and get the data and I process it in very, very large chunks. There's going to be some latency in the ingestion of that data. There's also stream. So stream is more focused about a real-time ingestion. It's processing as it arrives. Now, the challenge with stream, I have to consider, well, how do I match that scale? Imagine it's IoT devices. There's millions of them sending me temperature readings. That's very challenging. So with stream, you'll actually very commonly see different types of hubs sit in between it. It could be, for example, an event hub. It could be IoT hub. That's used to get all the ingestion coming in. Then it might actually use Azure Stream Analytics to process that and maybe do some alerting. Hey, temperature spiking over here. We need to do something really, really quickly. So there's specialist solutions around these, but the whole point is we have all of these sources. So we have data coming in. So we have to extract. So we have to read in the data and get the data out of whatever protocol or format that data is. Now what used to then happen was we would transform. Now there's many types of transformation we can do. I can think about mapping. So mapping is, well, there's this field in this input data goes to this field on the output, and maybe more complicated expressions to combine things. I could think about, well, there's wrangling. Wrangling may be tidying up the data. It might be getting to a set standard, so dates are always like this, removing bad data, making nulls in a certain format. There's different things I might want to do here. I might have more complex types of transformations and analysis I want to do. That's where I might use things like HD Insight. I might use Databricks. But there's things I'm doing to the data to get it into a different format. And the reason we would do this and then load it into something is, well, disk space was really expensive and I wanted to just have what I cared about. However, disk space is got a lot cheaper. And the problem with this transformation, we're transforming it. We're getting rid of stuff. We're only keeping what we care about today for today's requirements. What about if tomorrow I have a different set of requirements? So it's actually very, very common now to actually also add extract load transform. Then there'd be another load at the end. This takes, so let's say we have a data lake. It's a lake, I promise. Data lake. So for example, Azure Data Lake Storage Gen 2 would be an example built on Blob, remember? We would take the raw format and save it. And then it also carries on to the next phase. Because the whole point of this is, I might in the future have some new type of analysis I want to perform. I don't know what that is yet, but if I've transformed it and thrown stuff away, I can't, it's gone. So I'm going to keep it in the original format. Now there are some solutions that this raw format, it could be like a Parquet file. So a Parquet file is actually this columnar type storage. It can mount it as an external table and use it in analysis over here. I don't even have to bring it back into something else. Certain solutions will actually give me an external table to a file in my data lake and let me use it. So there's many different things that I can have there. So Synapse is an example that can do that external table. This is optional, it depends, but it's become very, very common. So again, we map it, we ensure the quality. We're basically getting the structure that we need to then move forwards. Then we're going to load it. We're going to load it into a database. Maybe then we can do something else, a data warehouse. We might perform, might be Cosmos DB. Different things. And then typically we'll then run the analytics against it. For example, Power BI. Power BI is a very common tool to run analytics, to create the semantic models, to create visualizations, to get the insight I care about for this data flow. So the whole point is we have all these different things happening for data. Data is huge. Data powers most of what we do these days. So we have to think about from the source to the sink. So we have data lakes for that raw storage. Azure Data Factory is very commonly used for the control flow. And then various data services are used for manipulation and everything else. Because all those different steps I showed, well, something has to do all of this. So there has to be an idea of a data pipeline. So there's some pipeline that's powering all of that. And the solution is Azure Data Factory. Now, I want to be super careful here. So Azure Data Factory encompasses the pipeline, but its focus is the control flow. What does that mean? It is not changing the data. It is orchestrating and calling things which they may then do things on the data. That's the whole point. So Azure Data Factory calls activities. So it says, hey, you now need to run and do this mapping. But it itself is not doing anything to the data. The activities it calls, they may claim the data. They may map the data. Azure Data Factory does have some native mapping capabilities. It can integrate with like Spark solutions to actually do richer transformations. But it itself is focused just on the control. Taking the data from the source through to the sink to get all of these various things happening. It itself is not typically changing the data. It's calling things that does that. So that's just an important point to understand around that. So that was the database side. So I wanted to finish just talking about artificial intelligence, machine learning. And when we think about these, Azure has a whole number of different services around AI, including machine learning. And when I think about what these are, just at a higher level first, let's go over here. Do I have space? Oh, did not mean to do that. Let's go back again. I did something very, very weird. I think I closed all of my screens. That was a mistake. So I can close all my screens. Let me get my whiteboard back for a second. So apparently if you do the pinch on the screen, it closes everything. That was very strange. All right, so let's go over here on this space. So I'll talk about artificial intelligence and the machine learning. Now, sometimes those two terms almost get intermingled, but they do mean different things. So I want to walk through just super quickly what those differences between them actually are, because it's important to understand what the differences are. So artificial intelligence. Well, firstly, I can think of, I'm going to have my robot. So I've got my robot. It's got its robot mouth. Robot eyes, very important. Robot ears. And then it's got its brain. It's got its digital brain. And the whole point around, I can't draw a brain. As we see, I can't draw many things. The whole point around AI is it's emulating, performing some human intelligent behavior to solve a problem. So that's artificial intelligence. Now, artificial intelligence, I may program the rules to facilitate how it actually does that. But machine learning is a subset. With AI, typically, I'm telling it, here are the rules, here's how you're going to exhibit this human intelligence. With ML, I don't give it the specific rules. I don't program them. Maybe it's beyond my capability to do that. Instead, we have how do our brains work? Our brain is a neural. Neurons connect. We learn things. We learn to pick things up. We learn to recognize things. We form pathways between the neurons in our brain that help us do things. So machine learning, it has a neural network. It has exactly the same idea of it has some inputs, and it has these deep internal neurons that have all these connections between them. It forms these pathways to give us some output. So it creates its own neural network, and it does that by we train to create a model. The model can then be used to predict. So that's machine learning. I don't tell it what the number one is. I show it a whole bunch of pictures of the number one. And it learns what is that. So I give it correctly labeled things. I give it conversations. And it learns the structure of the language. It learns what should come next. It learns a probability of what word would come after this word. But I didn't particularly tell it that. I'm just feeding it. I'm training it information. I might refine the model. There were lots of different stages. GPT is obviously huge right now. Well, you give it a whole bunch, you let it scour the internet. And then you might give it more structured examples of interactions between a human and how the bot should respond. Then there's reward functions where the human says, oh, I like this response, or I didn't like this response. How far back in the history you can go to view things. That's all part of the training and how it works. It's predicting what should come next based on the history, inputs it's given, and its model. So it predicts what word, and then the word after that, which gives it the impression of it's talking sentences. So these are very, very common things we're going to have. If I think about the types of services, we have Azure Cognitive Services. So a very common one, obviously, is going to be vision. So if I think about the vision side, there are many, many elements to vision. So, okay, we've got the eyes, scanning. There's image classification. This is a tree. That is obviously not a tree. There might be image analysis. image analysis, it will help me understand what's happening inside this. Oh, so it's a person walking under a tree flying a kite. There might be object detection. So in object detection, it's, hey, I'm giving it a picture. And hey, maybe there's the tree again. And there's also a car. That's obviously not a car, but let's pretend it's a car. And it puts a box around the object. Oh, tree. Oh, car. There's semantic, so that's that one. Semantic segmentation. And we see this a lot when we see these idea of artificial vision systems. It looks really, really cool. So in this case, it might be exactly the same picture. I'm just going to draw it the same. It's exactly the same picture, but instead of drawing a box around it, now what it would do is it would say, it would color in the pixels. Tree. It would color in the pixels. Car. So it makes it easy to see the exact parts of that. There are services, so that's that one. Face services. Now, this may just be as simple as detecting a face. There's a face there. It may be analysis. And this was fantastic. You tend to see less of the analysis. Obviously, in today's world, there's certain dangers. Features should work the same for everybody. And so some services have been dialed back in what they will say. For example, stating gender. That could be very problematic today. Age, race. So a lot of times you won't see, I remember once before that though, I went through and it was like hair 0%. It's fantastic. Bald, 100%. But it could do like, oh, happy, sad. So it could detect certain elements of the face. There may also be a step beyond to recognize. That is maybe recognition in terms of famous people. It may be recognition, hey, I want to unlock my car. We see it with our phones, hey, we do a facial recognition. It could be optical character recognition. Zero a picture, find me the text, say what it says. I might take it a step further to show it a form. So you look at this form and read in the content and put it into a database for me. So there's different things I might want to do there. A very huge one right now, obviously, is language. And this is super interesting. Understanding language. So different language models. Now, understanding is natural language processing. This could be the ability to sentiment analysis. Am I happy? Am I positive? So I can have things like the text analysis. So again, sentiment, positive, negative. Identifying entities within some body of text. Identifying key phrases within some body of text. And this is important when I start thinking about what should I pay attention to. And again, GPT right now, a huge part of the advancement is, I think attention is all you need was the title of GPT v2. But it's about what do you need to make it efficient? And it's what do I need to pay attention to as part of my interactions? What was the important part of all of that? Maybe translation services as well. But this has got a huge set of things all around right now. There's also, obviously, speech. And for speech, this goes both ways. So it can be, hey, someone says something, and I want you to make it to text. It could be, I want you to read out what's been given to you. It might be, I want you to translate. So that's an important part. But also, this predict, this ability to predict, this is decision making. This is huge. If you think about looking for anomalies, hey, some machine equipment has got an imminent failure, huge amounts of just regular Azure services are using this to say, hey, your CPU usage is outside of normal. Hey, I'm using machine learning to detect when you normally get busy. I'm going to auto scale ahead of the event. I'm going to alert you when you're outside of your normal thresholds. So there's a lot of different things that are, yes, I can have particular models and particular cases around decision making and prediction, but also a lot of other Azure services are just leveraging this as well. There's also specific services. So Azure Cognitive Services let me use basically all of these things. I may not want all of them. I may want to maybe break pricing down into particular services. So there are specific services. There are things like Azure Forms Recognizer. There is Metrics Advisor. There's a video analyzer for media. I use it as part of my subtitle creations. There's a bot service specifically designed that I have a certain knowledge base of information. You can interact with it, the chat bot, and it will give responses before maybe going to a human if required. There's Azure Cognitive Search for indexing data and documents and getting me insights from it. But there's also now the Azure OpenAI service. This just GA'd. It's February 2023 when I'm recording this. This is based on the partnership Microsoft has with OpenAI, the people that bring you ChatGPT. And their 3 services are now available as part of Azure OpenAI. So one of them is GPT. So GPT, I think it's 3.5, is all around that predictive capability of what word should come next based on some history. And a huge part of the capability is it now has a pretty deep history it can relate to, so you can have an ongoing conversation. It has a huge amount of parameters based on data it's learned from scouring the web. And then it can predict what word should come next, and then what word after that, and what word after that. So if you keep predicting what word should come next, it's a sentence, and it's a paragraph, and it's writing you songs. But it's all about predicting the word that should come next based on its history of knowledge it has, and what should it pay attention to focus on creating that interaction. So it gives it the appearance that it's intelligent, but it's really just using a model that's been trained to predict what word should come next. Now, you could argue that is intelligence. As humans, when we talk, we're really just predicting, hey, based on our history, what word we should say next that makes sense. Not going to debate that right now. But there's also Codex to generate code. GitHub Copilot is a great example of this. There's the DALL-E 2, the image generation. You can describe something and it creates a picture for you. So I can go and leverage all of those different services. So I guess I should just flip through this vision. I went through these on the whiteboard. There are also specific ones. And of course, there's the partner through the Azure OpenAI service. And that was it. So as always, we covered a lot of different things. Again, I would stress that the DP900 study cram and the AI 900 study cram go into more details around these things. But it's just important to understand the types of service when I might want to use them as part of my solutions. And don't underestimate the power of these AI solutions now. Like more and more times, there's some ability to maybe, especially the prediction capabilities, this new language capabilities, and combining that with these models to learn what should come next. I can tune those GPT models to something specific to my industry to help create a chat service for my customers, for example. I think this is really powerful. And this ability to have the machines apply intelligence based on what they've learned to help us be more efficient, there's just a huge scope for how that can help. So that was useful. As always, till next video, take care.